In the previous video, we work with the Cartesian tree. We implement the merge and split functions. So actually this is the basic functions, and using these functions we can very easily implement the insert and delete function. And this is the topic of our video. And let's start the insert function. What we have? I think we have the type signature like this. We have this binary tree of the pairs of A and B, and we want to insert a pair of A and B. And as a result, we want to receive a binary tree of the pairs. So actually our Cartesian tree. And of course we need orderings here. Orderings on B and orderings on A. This type class constraint. We need to do the comparing. Okay. Insert. What if we have empty tree? The simplest case, we can start with it. And we have some pair. And this way we defined as a pair. We have just one node in our tree, and we can construct it very easily. Otherwise, more interesting case, if we have some tree, of course I need to do a pattern match here. So I need to pattern match my pair X and Y, and I need to know the left and right subtrees. Also, I want to pattern match my inserted X and inserted Y. Okay. Okay, having this information, what we can look at our, we can compare where inserted Y and our root node Y. If our inserted Y is greater when our root node Y, this means that we need to use our inserted node as an root. This is a new root because it has the maximum Y. Okay, so we can define, in this case we can define our function as a function which have this pair and has and here we need to define the left and right subtrees. But also we have this old Y. Okay, we have this, what we have? We have this new root with Ix and inserted Y. We have this left subtree, right subtree, and we have this X and Y. Now we need to create new left subtree and new right subtree from these elements. So actually we didn't need to look such deep inside this tree. We can take this tree at all as T, and we can just split it by Ix into left and right subtrees, and this actually will be our new subtrees. Okay, so I can define it like this. I can define the new left and new right. and defined our new left and new right as a result of splitting. So we have split function which takes tree. Look at its type signature. A split function which takes some tree and element and produce a pair of trees. So I provide this function tree and element, and our split element is ix. Yes. Otherwise, if our inserted y is less than y. In this case, this means that our root node stay as it is. So we can define it like this. And here we have the left tree and the right tree. And we need to find where to insert, to the left or to the right. Okay, our pair. So we can mark this pair at all as one element, as one argument. And here we need to define in which of the direction it goes. So let's just define the new left 2 and new left new right 2 trees. And here I will define them new left 2. So how we define the new left 2? So with this is defined by we must compare our ix with this x, with ix with this x, and if our ix is less than x, when we defined our left tree with recursion, so we do the insertion into the left tree, we insert our ix. Okay, and otherwise we must insert it to the right and our left tree stay as it is. Okay. Okay. And in the similar way we define the new right tree. If our inserted x is greater than x, then we insert to the right our ix. Actually, we don't insert, of course, ix because we insert a pair, so we need to use pair here. And otherwise, our right tree stay as it is. Okay. So as always, this is conflicting names. Let's do the renaming. I will call this function as ins. I think this is enough. Ins function. Okay, now let's demonstrate how our function works. So what I need, of course, I needed first construct some binary tree, Cartesian tree. So we have this data. I think I can use this. I can use this to construct the binary tree with this data, and I print it. So I have this tree. This is the Cartesian tree. Let's name it as T. We can print it. And let's now insert into our tree some new pair. This new pair will have, so what we have, we need to, I assume that all our x and y is unique. So I need to insert, for example, here 7 and let's take the pair 7 and 10. Okay. Of course, I need to reload it first. Okay, we built our tree, we print it, and the insert. So when we do insert, we construct a new tree. Let's print this tree. Okay. As you can see, this is correct. Yes, correct. Correct. Cartesian tree. But let's, for example, from this data, I will remove the 4 and 7 and put, for example, 7 and 7 here. And I will try to insert, for example, 4 and okay, let's move 8 here. Can I insert 4 and 6, for example? Let's try in this way. So we need to insert 4 and 6. Okay, so we have this, and after insert we have this. As you can see, this is correct. Yes, correct. Yes, this is correct. Now let's implement the delete function. What is the type signature? I think the type signature of delete function exactly the same. I will call it del function. Let's take some by tree, some pair to delete, and produce a new deleted tree. What we have is the delete from an empty tree. No matter what we delete, we can say that there is an empty tree as a result. But what if we delete from some tree like this, which we can pattern match like this? And we need some pair which we want to delete, like this. Delete x and delete y, delete x and delete y. Here we can, so what we need to do, we need to compare the x with our dx. So if it is equal, if this x is equal to dx, and y is equal to dy, when they can just remove this node and we have this left and right subtrees, and we have the function to merge them. So actually we do the merge under this function. Note that left and right subtrees follow the constraint which we need, that every left x must be less than every right x, and that's why they can merge our trees. Otherwise, of course, if we have another case, well, they need to check. Actually, our Cartesian tree is a binary search tree, and we can use x to move to the left or to the right. So if our x is greater than our dx, well, we can define our tree as it is. I can use node here, marker. So I can define my node as it is, and let's mark it as a pair. We have this pair stayed the same, the left tree also stayed the same, but the right tree we can define the recursion. So we need to take right tree and remove the deleted x from it. Actually, not the deleted x, we need, of course, deleted pair. So, another case, then our x is less than dx, then we do exactly the same thing, but in the left. Okay, and right stay the same. Okay. And I think we catch all the cases here. Let's reload and print our build our tree, print our tree. And what if I want to delete from this tree the pair, for example, 5 and the root pair, actually 5 and 8. Let's print this. Okay, I delete the 5 and 8. I delete this node, and as you can see, we have the correct Cartesian tree. Of course, I can try to remove, for example, 1 and 2. I remove y 1 and 2, and it is stay as it is. Why this happens? This is strange. What if I remove 2 and 4? This is very... Okay, what I'm doing wrong? So it's remove root, but doesn't remove any other node. As you can see, I think I do some errors. And of course I do errors because I do the symmetric error here. So if our dx is greater than x, then they go to the right, and otherwise we go to the left. I think error was in this case at this point. Let's reload. Let's build our tree. Let's print our tree. And let's delete. What if I delete 1 and 2? Okay, as you can see, it removed this note, and so it works, I think. Yes, it works. Yes, so we done the ventilation. And I think that's all for today. Thanks for watching. I think in the next video we'll implement the something like the Cartesian tree with the implicit key. And thanks. Write comments, push like, push subscribe, and see you in the next video. Bye bye.